All right, let's begin with a word of prayer. Dear Heavenly Father, we just thank you for a semester we're about to start, and I thank you for these students. And we thank you for your creation that we can study and understand a little bit of with differential equations. I just pray that you bless this class. Just pray that each student would get the most they can out of this class just to glorify you, Lord, what they do. In your name I pray, Lord Jesus. Amen. All right, so I'm just going to dive straight into it. You know, I have syllabus. It'll be posted a little bit later. It says exciting things like there's a test. You all have to take it. There's homework. You should do it.
Wear pants instead of shorts.
What's that?
Wear pants instead of shorts.
Where? Oh, I don't have that. What are pants? I mean, shorts. I mean, I know I'm supposed to kick students out when they're wearing shorts, but it's just not in my DNA. I wasn't raised here. Like, shorts don't offend me particularly. I mean, if one of you was to wear, for example, a pair of purple pants, it would be much more offensive to me than shorts, just as a point of reference. But, yeah, that's my upbringing. I don't know. Violent immigration of purple pants. On men. So, these are the kind of antiquated notions that I still harbor. All right, let me stop making microaggressions and focus on some more major ones. So our first topic basically is first order differential equations. All right, now, I may give you a little bit of the big picture here. I guess before I even get into that, I should just talk a little bit about what is a differential equation and what are some important terminologies for a differential equation. So let me back up a step here and just say, before I even get, that's our main course for today. What I want to talk about, start with just what is a differential equation. So, what is a differential equation? It's an equation which involves derivatives. I mean, that's kind of it, all right? So some examples. Differential equations. So I usually use this silly abbreviation. My abbreviations have decayed somehow. Is there a glare in here? Maybe not. There's got to be a way to make these things go down. So some examples. How about this? dy dx equals to, say, 3y rather. You can have dy dx equals to y squared. Now, a lot of times we like to write something like, instead of writing dy dx, we might write, y prime for this. All right. These are both actually first order differential equations because they only involve the derivatives up to first order. The first one is a so-called, actually it's an example of what's called a linear differential equation. The second one is nonlinear. This is first order linear. This is first order nonlinear. Let me give you another example just to try to pick at this terminology a bit. If I had something like this, y prime 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 plus e to the t times y prime prime plus y equals to 0. Let's see here, let me describe this differential equation. What kind of differential equation is this? By the way, what does y prime likely mean here? It's kind of our custom actually to, if we write something like this, it should be understood that y prime actually means what? I've got an independent variable t here, right? So like y prime would be dy dt. All right? So sometimes we use x as the independent variable, sometimes we use t as the independent variable. Depends on the application, right? Now, this is what kind? Well, this is a third order, right? Third order. And you might think, I mean, e to the t, is e to the t linear? It is certainly not. Yet, this is still a linear differential equation because the dependent variables in the derivatives appear linearly. The thing that makes a linear differential equation, all right, is the following trait. basically you can rewrite this as L, which is equal to d cubed plus e to the t times d squared plus 1, all right? That's an operator. What's an operator? Well, it's a thing which takes functions in and spits functions out. It's a function of functions, as it were. And well, actually, I mean, for what it's worth, this is a smooth operator. I mean, songs have been written about this. And so the differential equation above, I have been known to do lectures to that song in the past. Let's see here, but I'm a little bit worried about copyright issues. Let's see here. L of y equals to 0 is the same, like what I wrote in purple is the same as what I wrote in green. That's that differential equation in operator notation. We'll be spending a fair amount of time this semester really trying to understand operator notation. Thinking of differential equations in terms of operators is a powerful concept. And so the key here to a linear differential equation is this really, really cool property that if you have y1 equal, if you have like, if you have this, let me put a little j here and say that this is for j equals to 1 and 2. All right, so if I have two of them, y sub 1 is a solution, y sub 2 is a solution. Wait a minute, solution, what's a solution? This is not profound. A solution is something, it's a function that when you plug it into the differential equation, it works. All right? So if y1 prime 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 plus e to the t times y1 prime prime plus y1 equals to 0, that makes y1 a solution to this differential equation. And if I have y1 and y2 are solutions, since this is a linear differential equation, we have this just wonderful thing, which is if I take a constant and another constant like this, well, you still have a solution. So a linear combination, all right, of solutions is again a solution for a linear ODE. This is part of what goes into this superposition principle that we'll talk about this semester. It's not all of it. This is, well, let's see here. If I take this equation, our first example, and I rewrite it just a bit, we get to dy dx minus 3y equals to 0. So that's kind of the more the standard form for a linear ODE. What's an ODE? These are all ODEs at the moment. The O is for ordinary. Ordinary. And the DE, well, that's kind of explanatory. I mean, it's a differential equation. What makes an ordinary differential equation an ordinary differential equation? This P is for partial. Ordinary differential equations are written in terms of ordinary derivatives. But to be more precise, really what we're saying, ordinary differential equation is one which has one independent variable. Partial differential equation could have 2 or 3 or 4 independent variables. I'll give you examples of those in a second here, but let me finish this talk here. A little bit more, I'm just trying to throw some terms at you here. Both my first example, let me number them. Say example 1, example 2, example 3, right? Both example 1 and example 3 are what are called homogeneous, all right? And I guess arguably example 2 is also homogeneous if I rewrite it, but I don't really think about homogeneous versus not homogeneous for nonlinear. This is nonlinear because the y squared here. All right, so what's an example of a non-homogeneous differential equation? That's important to your daily life. 2 come to mind right off, all right? Here's one example. Take a spring, right? And stick a mass on it. Put some dude over here. Let him put a force on it, F naught, right? And then the spring goes back and forth, and according to how the lister top hat pushes on it, right? Newton's second law. So there's different forces that are on the mass, right? You draw the free body diagram. You have, let's say that he's let's say he's pulling on it, all right, with a rope or something. So you have force F naught that way, right? We're supposing, and then there's some kind of friction force, which is opposite its motion, right? So the friction force, a good model of that, something like, I don't know how to, I mean, the arrow doesn't mean much, I'm just drawing it this way for the sake of my, so something like B, BV, where V is the velocity. And I'll put a minus here because if the velocity is, if the motion's to the right, it's positive, right? So the friction force acts to the left, right? So that would be the, the friction force would look like that. And of course there's the spring force, right? Hooke's law. Hooke was apparently a contemporary of Newton, but you won't find mention of him in Principia because I guess Newton didn't care much for Hooke's work because it was very sort of fuzzy and not quantitative. Newton was kind of big on specific equations, well, calculus eventually. Anyway, so those are that's a kind of bad free body diagram here. And so what do you say? Well, you have MA, right, is equal to what? It's equal to the external force, F naught. This should be a minus kx, technically, because if you think about x being positive, if x is positive, then the spring is pulling back, right? It's going to the left. If x is negative, then the spring is compressed and the force is that way. So minus kx and then minus bv. All right. But what is A, what is V? Well, typical physics notation, something like this, V is x dot, A is x double dot. So this dot notation, which you could write as x prime, or x prime prime in typical differential equation speak. And so if I rewrite the spring force law, this is a spring under friction with an external force. What do you got? Well, you got x prime prime plus bx prime plus kx equals to F naught. So again, what I'm trying to do right now is just to give you a lay of the land and give you a sense of what differential equations concerns and the terminology that you want to start to try to familiarize yourself with so you kind of know where you are, right? Again, we're going to go back to first order differential equations here very shortly and we'll focus on that most of this talk. But just some terminology to get us kind of going. So here M, B, and K are constants. This could be a force variable with time, right? Mr. Top Hat could be like pulling on it all kinds of different weird ways. And so this is what's known as a second order. It's actually constant coefficient, linear, because x prime, and x are all linear appearances of the derivative, right? Linear ODE, second order, right? Second order, and it's non-homogeneous because of the forcing term. Right? And there, the forcing term is literally a force. Right? As we go on and study problems more abstractly, we'll still call that a forcing term, even though it might not be a force. Do you guys happen to know where this mathematics comes up in other applications you're interested in? You might be interested in. You should be interested in. You will be interested in. Right. How about this guy? An RLC circuit, right? So here's L, here's your R, here's your C. If you write Kirchhoff's voltage law for that loop, it's the same thing. It's a second order differential equation in the charge, for example, on the capacitor, where the coefficients are given by, it's almost RLC, it's not quite that. But I'm not going to do that right now, but I'm telling you, here the voltage source plays the role of an external force. Mathematically, it's the same problem. Okay, so anyway, just a little bit of terminology, a few examples of ordinary differential equations. Partial differential equations. What are important partial differential equations? Well, here's an example of one. How about this? Del dot E equals rho over epsilon naught. So let me expand on that. That's partial x ex plus partial y ey plus partial z ez equals to rho over epsilon naught. Rho is the charge density. E is the electric field. X, y, and z are the respectively x component, y component, and z components of the electric field. This, anybody happen to know what this one's called? This is Gauss's law in differential form. Right? This is a partial differential equation. As you can see, it involves derivatives with respect to x, y, and z. Those are taken to be independent variables. This is a PDE. All right. Let's see here. Since the electric field is equal to minus the gradient of the potential function, you guys probably usually use V for potential, like voltage, right? Some people use phi. If you take this, right, and put it up in there, what do you get? You get del dot minus del V, right, is equal to rho over epsilon naught. And so what this gets you is that the Laplacian, del squared of the voltage, is minus rho over epsilon naught. This thing is called Poisson's equation. In the absence of charge, when the charge density rho is 0, this gives you something called Laplace's equation. Book after book after book after book, careers have been filled solving Laplace's equation in various contexts. It's a very, very well-studied problem. But anyway, these are all PDEs, and it goes on. Like fluid physics, if you study this fundamental differential equations that govern fluid flow, those are partial differential equations. I mean, if you just start thinking about applications, most things don't depend on one independent variable, right? There's lots of moving parts. And so it's very common when you study a physical or an engineering problem, at its base, it's going to be a partial differential equation. You're like, well, partial differential equations are so awesome and so interesting, why don't we just study those? Why waste our time on these, right? These ordinary differential equations are so ordinary. Well, there's a simple answer to that. To solve partial differential equations, you need to have a mastery of ordinary differential equations. And so that's where our focus will be. In the past, I have tried to teach PDEs at the end of this course, like the last 2 weeks, but in recognition of the general decline of calculus skills among students, I have removed that from the course, and so now your course is a little bit more lackadaisical than this was last time I taught it, for example. Don't misunderstand that to mean that this course is easy, though I think it's not that hard. My opinion doesn't matter. So. All right, so anyway, let me stop talking to you about these flowery generalities and give you some specific examples. In fact, I'll start with this one. So basically what we're going to do this semester is we're going to look at various techniques for solving ODEs. All right, to start with first order ODEs. Then our next thing we'll do is we'll look at how to solve nth order ODEs, like second or third or fourth order ODEs. Much of that will be based on operators and properties of operators that will be very interesting and simple. Then, after that, I forget exactly, but after that we'll study systems of differential equations. What happens when you have several ODEs and you try to solve them all at once, just like when you have several linear equations and you try to solve them all at once, guess what? To do that properly, you need eigenvectors. So we'll learn what an eigenvector is and how to work with them. Do a little bit on systems there. Then we'll spend a couple weeks on Laplace transforms, which are, of course, very important for engineering and other things. And let's see here. Oh, and then at some point I should talk to you guys about what are known as energy methods and visualization. That may come a little bit earlier. Energy methods and visualization, in contrast to the other things I was just talking about, those are ways of sort of gaining an appreciation for the behavior of a differential equation without actually solving it, all right? And it's important also. So, I mean, you can't always solve a differential equation, right? So it's nice to have, when we can't actually just solve it, some other way of understanding it. So that's kind of the course in a nutshell. I'm sure I forgot something, but I will post a syllabus tonight and you can look at this. Oh, sorry, I should erase that too. So, first order differential equations, there are three methods, basically. Ignoring the special substitution stuff, which I'll probably get into next time. But there are three basic methods that I like to talk about. And I guess the fourth is the thing I'm talking about next time, perhaps. But the first method is separation of variables. All right. The second method I usually talk about is the so-called integrating factor technique. Now, if you had calculus 2 with me, you've already seen both of these in Calc 2. I think Dr. Skimboris also teaches integrating factor technique in Calc 2, and maybe everybody else as well. And then exact equations. No one in their right mind would teach this in Calc 2, as it requires an understanding of Calculus 3. I teach some of that when I talk Calc 3. All right, the fourth sort of bag of tricks is substitutions and special problems. But to me, that these are the central main plans of attack we have here. All right, so example 1. dy dx equals to 3y. Actually, that's too boring. I'm going to add an x. So how do you solve this? Well, I'm kind of laid it out for us, so you kind of could guess what method I'm going to use. Method number 1. Okay, so method number 1, separation of variables, is just what it sounds like. We separate variables, dy over y is equal to 3x dx, right? And then integrate both sides, right? The integral of dy over y, you probably don't know. I'm sorry, I shouldn't be so pessimistic. I just got done grading a prerequisite quiz for Calculus 2, and it's rough. It's rough in there. But it's okay. They'll get better. It's just the first day. Let's see here. 3x squared over 2 plus a constant. Oh, but I really should add different constants on the different sides, right? In fact, after you do this once, you regret it, and then you're like, wait a minute, that was dumb. I could have just added one constant on one side. It would have been just as general, right? So instead of saying C1 and C2, I just usually, from this point on, I just say, well, 3x squared over 2 plus c, you know? Because this c would be like C2 minus C1. And as a general rule of thumb, it's a first order differential equation. You only really need one constant to characterize the ambiguity in the general solution. This general solution is not actually a specific function. It's a whole family of functions, right? Why is there a whole family of functions? It's because to pick out a specific solution, you need a little bit more data, right? You need an initial position. Once you have an initial position, you can kind of imagine that there's one solution that goes through that. Like a rough picture of that is something like this. You could take this differential equation, right? And you could plot the slopes that are indicated by this at different points, right? And now if I had my computer, I could show you, there's something called p-plane that would give us a way to do this specifically, or maybe Mathematica, I don't know. So, you know, you could draw a little so-called isocline plot for this sort of thing. This is not what it looks like. I'm just making one up, all right? The point is, once you have sort of one, you know, data point, that's your initial condition, then you just kind of try to fit a curve through there that sort of will follow the slopes. And so the point is, once you pick that initial point, then you fix a particular solution. But otherwise, the C here allows you to toggle through different possible solutions, right? A different choice of C maybe would put you down here or something. I don't know. All right. Sorry, I should have tried to draw the isocline thing for something which is less intimidating than this one. I'll come back to this again in my favorite example. Now, a little bit of terminology. A lot of today is terminology. I hope you aren't bothered by that. But we have to be able to talk to each other, right? I don't want you to get to the test and then read my requests and then go, what on earth is he talking about? What in the world is an implicit solution versus an explicit solution? This is an implicit solution. So an implicit solution is me being nice to you. Implicit, if I say find the implicit solution, all right, and my custom, by the way, is if I just say find the solution, I mean an implicit solution, all right? My default is implicit solution. Explicit solutions are a rare and wonderful thing in the world of first-order differential equations. There's tons of differential equations that you can solve where you have an implicit solution, it's pretty easy to get your hands on, but an explicit solution is just about impossible to get. This one's not that. Like this, I can solve for y. Solving for y gives me the absolute value of y equals to the exponential 3x squared over 2 plus a constant, right? Now, you guys know laws of exponential, right? This notation is just e to that stuff, but is that okay? Okay. I know some of you have had classes with me before, so you know how I roll or whatever. But others of you are familiar with my mistake. So this absolute value of y, of course, is plus or minus y, right? And so you can take this plus or minus and you can roll it into this, well, attach it to the e, and then you get like plus or minus e to the c. Well, what's plus or minus e to the c? That's just an arbitrary constant, right? So, tilt your head, squint, and you can see that this is really y equals k exponential of 3x squared over 2. There you go. That's the explicit general solution. Explicit general solution right there. Now, question. What's the one value k shouldn't be allowed to take? I mean, k is apparently, in this derivation, k is equal to plus or minus e to the c. That's plus or minus, what is e to the c? Is it positive? Is it negative? Is it 0? What is it? Exponential of a value.
It's positive, isn't it?
It's positive, right? So plus or minus a positive thing is certainly, it's not 0, right? K shouldn't be allowed to be 0. Do I have to write to the side of what I just boxed, k not equal to 0? I mean, on the basis of the separation of variables argument, yes. But on the basis of logic, no. Because if you go back to the original question, which was to solve this differential equation, check it out. Is y equal to 0, does y equal to 0 work? Is y equal to 0 a solution? Because putting k equal to 0 makes y equal to 0, right? Identically 0. It's the constant 0 solution. Check it out, it works, right? The derivative of the 0 solution, 0. 3 times 0 times x is 0. 0 equals 0 for all x. Good, we're good to go. 0 works. So 0 was lost. How did we lose 0? 0 was lost in the separation of variables technique because we divided by y. Which means once you divide by y, you're going to lose the y equals 0 solution logically. Pretty good chance of it. But the quirky thing is, in the process of finding the general solution, you put it back in if you're sloppy about the k. The math is forgiving here, right? All right. Let me work another one of these. Here's one of my favorite examples. I think I blathered on too long about terminology at the start, so I'm a little bit. What do we have till? What's our 12:30? Okay, we're fine. We're fine. So let's see here. Another example. dy dx equals 2 minus x over y. All right. Yeah. So by the way, just again. In terms of your studying, I would like you to be reading my notes and working through my notes. Always, pretty much, but especially at the moment because I'm in the book, right? So I will send you an announcement tonight with that. If you don't wait for me, though, it's already on the webpage. If you go to my differential equations webpage, the notes are posted there. I think those are notes from 2014. I'm not really going to change them. The notes refer to a textbook. Oh, sorry, I'm distracted. Don't be distracted like me. I referred to some other textbooks that have been used in the past, but you can ignore that. I mean, we used Zill, we used Ritter and Rose. I used Nagel, Staff, and Snyder before those. So Nagel, Staff, and Snyder is a very good book. We'll definitely go with that this semester. Anyway, my point is you should be looking at the notes to supplement this and to try to get going. All right. I've got something like 20 examples of separation of variables in the notes. Okay, so here we go. Separate variables, we've got y dy equals minus x dx, right? And here, let me show you a trick. If I integrate this, well, oh, fine, I won't do a trick. Let me behave. What do you get fine? Integral y dy equals minus integral. So you guys know how to do these integrals, right? And I don't know, it looks like the constant here should be called r squared over 2. Just guessing. I don't know. And then okay, so then what we got is we've got x squared plus y squared equals to r squared is our implicit general solution. Now, my labeling of the constant in this rather weird way was for my own self-serving reasons, because obviously the solutions to this differential equation are concentric circles about the origin. If I was to try to draw the sort of isocline plot, the direction, indicate the slopes which are given here, what does minus x over y do? Well, it's 0 when x equals to 0, right? It's undefined here, right? But it's going to be like 0 here. So you've got like these horizontal slopes like here. You've got vertical slopes like here, if you look at it in a limiting sense, all right? I guess technically speaking, the differential equation is not defined when y equals to 0, So, and then in between you've got these kind of deals. So this is not the sort of thing I should try to do freestyle, but you don't have to do too much before you can see that if you try to connect the dashes, so to speak, you get, and I really should have drawn the circles first if I was smarter. Oh well. But these are the solutions. These are the solutions to this differential equation. It's concentric circles about the origin. Now, I would point out, as a point of order here, that these are really the solutions. I mean, I would say there's a different way to write this differential equation. You could write it like this. You could say y dy plus x dx is equal to 0. This is the so-called Foffian form of the differential equation. So this formalism, which you may be less familiar with, probably are, is great because this formalism doesn't pick sides, right? I mean, once you write dy dx, it's like y is the dependent variable, x is the independent variable. And then you've got this pesky thing called the vertical line test, right? But that's so artificial. See, because circles don't care about which is x and which is y, they're circles. So a better formalism to capture differential equations like this is this Foffian form, which treats x and y symmetrically. Okay, anyway, a couple of examples. So I think you guys can do separation of variables, right? Not a big deal. You did in Calc 2, some of you, right? Was it bad? It was one of the more pleasant parts of Calc 2, I think. Yeah. It's certainly not nearly as unpleasant as like convergence and divergence, right? In fact, nothing in this course is as unpleasant as convergence and divergence in the mind of a student, I think. And that brings us to number 2, or example 3. Could I find an explicit solution here, by the way? I mean, only locally, right? So if I said I want an explicit solution like up here, I could have done something like y is equal to the square root of r squared minus x squared for appropriate r, right? But if I wanted an explicit solution down here, then I need something like y is minus the square root of r squared minus x squared. So, you know, the business of finding explicit solutions is kind of a tricky business in general. If I ask for an explicit solution right here, couldn't do it. Not for y as a function of x. Now I could give you an explicit solution of x as a function of y there, but that's something else. Excuse me. Children make me sick. Or faculty orientation. I blame faculty orientation. My children are nice. Oh, goodness. I'm hoping this doesn't spiral. I mean, I hope this cough is temporary. Foreboding words. All right, so integrating factor technique is for a very specific kind of first order differential equation. Something like this. dy dx plus py equals to q. So what I'm going to do here is I'm going to work this meta example, and I'll work on the side over here. Example 4, I'll work a specific one of these, dy dx plus, say, 2 over x, y equals to answers. I don't know. I'll put in something here in a second. I'm going to fill in the blank here, right? It's, you guys aren't allowed to do this on tests, as I say, but I can't do it here. Okay, so the way to solve something like this, first of all, just a second, let me think what I should put there. I guess I could put like an x squared, it would probably be fine. I reserve the right to change that. Anyway, the point here is, if you try to do separation of variables here, can you do it? If I had more class time to burn, I would really try to do it, but you know, if you start playing with this and try to isolate y and x, you'll find that they're just stuck together here in an additive way, and it just doesn't, it's going to take something sneakier to separate y and x in order to integrate the problem, all right? So, let me show you how that goes. So basically the thing is, we invent this thing. You say, well, how did you know to invent this thing? Well, it's pretty simple. Somebody showed me how to do this. And now I'm showing you. So I is the exponential. There is a deeper reason, but it's not one that we can talk about here just yet, or maybe ever. The exponential of the integral of p dx, this is the so-called integrating factor. So for, you know, over here, we'll look at I equal to the exponential of the integral of 2 dx over x, right, which will be the exponential of 2 times the natural log of the absolute value of x, right? Which is, by the way, the exponential of the natural log of the absolute value of x squared. Yay, exponential of log is the thing again, right? And so this is just equal to absolute value of x squared, which, by the way, is just x squared. So the integrating factor for my example 4 is simply x squared. All right. Now, how does that help? How does that help? Well, I'm going to return to example 3 here and show you how it works at the meta level, and then we'll see how that gels for example 4. So, you know, if I calculate dy dx, what do I get? I get the exponential of the integral of p dx, right? Times the derivative with respect to x of the integral of p dx. What's the derivative of the integral? It's just p again, right? So, and this is just what? By definition, that's what is it?
X squared?
What's that?
Is it the x squared that we just found?
Oh, but this is a, I'm trying to, you know, I'm looking for it in terms of I and P. Ah, there, not good. I, this is just I, right? So this is IP. Oh, goodness gracious, I'm glad I didn't bring my son today. All right, so if we take, we call this original differential equation star, and we multiply star by I, what do we get? We get I dy dx, right? Plus IP y equals to IQ. So again, multiplying star by the integrating factor. Now here comes the really cool thing is if you look at this, right? Remember here, this is really what? This is really di dx, right? So what we have is we've got I dy dx plus di dx times y. In other words, this is the same as the derivative of the product of I and y. It's the product rule in reverse. And now that I have that, I can just integrate both sides, basically. I have the total derivative is equal to this particular function, and so this gives me that Iy is equal to the integral of IQ dx, and therefore y is equal to 1 over I, the integral of IQ dx, where I was defined as above. And there you have it. That's a formula that solves a linear first-order ODE for arbitrary P and Q, provided they're continuous. Oh, they don't even need to be continuous. I mean, P and Q can have jump discontinuities. You can still integrate them, right? Didn't use differentiability in P or anything like that, right? Now, I have various points in my teaching of differential equations. I've had students try to just memorize this, right? They're like, okay, so this is the answer. This is the answer to this differential equation. I'm just going to memorize that. I'm going to use that. It never goes well for these people because, like, the beauty of the integrating factor technique is it's self-correcting. If you do the calculation of the integrating factor correctly, when you get to this step here, it will actually be a reverse product rule if you think through it. If you've calculated the integrating factor wrong, this step, going from here to here, won't work. So we'll find out very shortly if that integrating factor is legit or if I made a mistake. So we just follow the general steps here. So let me number them so we can make a comparison. So step 1 was to calculate the integrating factor. Step 2 is to multiply the differential equation by the integrating factor. Step 3, reverse product rule. And step 4, integrate and solve for y. So we already did step 1. Step 2, multiply the differential equation by x squared. So we get x squared dy dx, right? Plus, what's x squared times 2 over x?
2x.
Yeah, okay, so x squared dy dx, you just told me, plus 2x y equals x to the 4th, right? Did it work? Is this, right? Is this really the derivative with respect to x of x squared, the integrating factor, times y? Take the derivative of that product. We get x squared times dy dx plus 2x times y by the product rule. It worked. If I calculated the integrating factor wrong, this wouldn't work. You go back to the integrating factor, you fix it if that happens, right? If you just use this boxed formula, I mean, I love the formula, it's general, right? But it's not self-correcting. This is self-correcting if you follow my advice here. And then, of course, we can integrate both sides. Integrate both sides, we get what? X squared y is equal to 1/5 x to the fifth plus a constant. Now, if I just said solve it, we'd be done. But if I say find the explicit general solution, what do we have left to do? So this is an implicit solution. This one's not that hard, right? To solve for y, we just divide by x squared, right? Now, people have a really bad habit of just dividing one of the things by x squared, but not the constant. Like, so many times I see people just write c here, but what you should write is c divided by x squared, right? That's what algebra gives us. There's the explicit solution.
Well, I mean, since it's a constant, does it really matter if you record the x squared?
Oh yes, because it's not just a constant, right? The solutions, different solutions to this differential equation. It's very, okay, so like, something I usually say, and I forgot to say at this point, is you guys have already been solving differential equations, right? I don't know if you thought about this or not. All of calculus 2 was differential equations. You're doing what? You're like integral, well, most of calculus 2, integral of f of x dx is equal to y, right? What is that? You're trying to find y, right? What does this y do? How do you judge whether y is correct or not? This is the same as saying, is dy dx equal to f of x, right? So every time you do an integral, you're solving that differential equation, that very special differential equation, dy dx equals to the integrand. That differential equation is very special. The solution set to it, they are related by translations. So like one antiderivative and another, they're just related by a shift, a vertical shift in the graph. But the structure of solution sets for more interesting differential equations is very different. Different solutions in here are not just vertical shifts, they're rather complicatedly related. Over here we've got circles, right? Like you can't take the sum of circles and get a circle again. These in fact are, oh, that's not a linear differential equation, this of course. And here the sum of solutions isn't a solution again either because there's this inhomogeneous term over here. Let me stop. Trying to put too much here in this comment. Okay, so that's the integrating factor technique in a nutshell. When do we use it? So separation of variables, when do we use it? This is going to be kind of stupid. We use for separable equations. So in other words, you have like dy dx can be written as f of x times g of y, right? So if the equation, I've probably misspelled separable. Here, let me fix it. Use it for separable differential equations. In other words, you can separate the thing that's given dy dx into the product of a function of x, a function of y, so you can isolate the variables, right? The integrating factor technique you use for linear differential equations of the form dy dx plus py equals to q. Okay, so in other words, linear, first order, ODE. Do you guys have any questions about this integrating factor technique before I go on? I have many more examples in the notes for you to study. I'll assign you ones to do so you can kind of internalize it. Maybe you have some fuzzy recollection from Calc 2. Joining us, anybody? I've got some of these, yeah, okay. No? Yes? Okay. I mean, the question I asked when I saw this the first time was, where on earth does this integrating factor come from? Like, you're just integrating the exponential, take the exponential of the integral of the coefficient of the y term. What? Why would you do that? I mean, it works, great, but why, you know? And what's the significance of that? Those are interesting, deep questions, yeah.
Can you will we be able to adjust the integrating factor based on the equation to solve other types of differential equations?
There are further integrating factor techniques, yeah, which we might talk about more another day. Like there's like 2 or 3 very well-known special techniques. It's the tip of an iceberg. There's a larger program of integrating factors. The reason that this one is what it is has to do with the so-called translation invariance of the differential equation. There's a book by Peter Hayden where he derives this. Well, no, I think it's Cantwell's book. These things I don't know that well, and they haven't been, well, in my opinion, they haven't been written in a terribly clear way for math majors. Maybe it's clear to engineers, I don't know. I mean, Cantwell's an engineer. He wrote this book on symmetries of differential equations. I did an independent study with a student a few years ago on it. But there's a theorem called Pfaff's theorem, which basically says that there is an integrating factor for any differential equation with very, very minimal assumptions about it. First order. But that ties into our third technique, which is exact equations. Pfaff's theorem actually says that you can take any differential equation in Pfaffian form. He probably didn't call it Pfaffian form. They don't usually, Galois group didn't call it Galois group a Galois group. He just probably called it a group. Well, he might even say called it a group, I don't know. Anyway, you take the Pfaffian form, you can multiply it by some particular function and put it into the form of an exact equation. Yeah.
So is there like a diluted version for why we're using the coefficient of y for the integrating factor?
Is that, again, I'm sorry.
But the question of like why are we using the coefficient of y as
Yeah.
the integrating factor? Like, is there like an easy explanation for that? Or
Not that I know of right offhand. I mean the most obvious explanation on the board because it works, but I know that not always the most satisfying explanation, but I don't have actually a good elementary explanation for why, what motivates the integrating factor. Maybe I should, I don't know, but I don't know that at the moment. It's probably a good question to ask. I suppose I could look for its significance by studying first-order differential equations, which I know the physical significance of. Maybe I could come to some understanding of what it is by doing that. I'll have to think about that. It's a good question. Anyway, much harder questions of motivation aside, the technique is pretty cut and dry. Calculate this thing, multiply it by a reverse product rule, integrate both sides, you're done. A few steps, but These are not mutually exclusive categories. There's overlap between these different techniques, all right? So, I get the most annoyed with students on 3. Because, well, I'll explain as we go here. It has to do with inattention to what is meant by the big F. All right, let's see here, the big F. So, if we have m dx plus n dy is equal to, all right, the total differential of some function f. So f is equal to a function of x and y, and I call this the level function. The level function. So what I a lot of times see students doing, just jumping ahead a bit, is they just put a box around f and go, okay, that's the answer. That's not the answer. Like, the solution is the answer for a differential equation, unless it's been asked differently. And the solution is not f. The solution is a level set of f. All right? That's the punchline here. If this, then the solution to m dx plus n dy equals to 0 is simply f of x comma y equals to c. I mean, this solution set, defines implicit solution to star. All right. Excuse me. So that's the theorem, basically. This whole discussion is built over. Now you would say, well, what on earth is df, right? Well, you've seen this in Calc 3. df is the total differential. So what this means is actually partial f, partial x, right? dx plus partial f, partial y, dy. Let me show you an example of this. What example are we on? 5? Yeah, okay. So example 5. If I have like 2x dx plus 2y dy, right, equal to 0. Is this an exact equation? In other words, can I rewrite this? Is this thing, right? Is this just the differential of a particular function of x and y? What combination of x and y can I take the total differential of and get back 2x dx plus 2y dy? Oh, I'm sorry. Here, let me make it easier. All right, I'm putting you guys out of your misery. X squared plus y squared, how about that, right? Because the partial derivative of this is 2x with respect to x. Partial derivative of this is 2y with respect to y. Total differential of x squared plus y squared is 2x dx plus 2y dy. So, what's the solution to the differential equation? X squared plus y squared equals to a constant solves star star. I'll call this thing star star. Give it a name. That is how to solve an exact equation. I could try to make it more complicated. I could prove the theorem for you. But I'd kind of rather just do this and come to an understanding with you guys at this level of calculation, because I mean, that's it. Any questions? I guess there's an obvious question, right? How did I get from here to here, right? I mean, I just guessed and checked, basically, right? Like, you made up the example, so match the other example. You have an unfair advantage. I'm like, fine, it's true. It's true, it's all true. You got me. Obvious question, is that free equation an exact equation? How do we know if it's an exact equation or not? You know? Any ideas? Excuse me. So it's a 1, right? No? Is it 12:30 or 12:45 this one? 12:45, nice try. Oh, no, 12:30?
Yeah, 12:30.
Okay, so I'm a little bit unnerved because, like, Dr. Wang earlier today asked his class when class ended, and they told him like 15 minutes before that it was class over. So I think about for an hour earlier today. I told them that you should get them back by going 15 minutes over next time. But probably won't. Dr. Wang doesn't have the will of fire. See here. So if m dx, right, plus n dy is equal to partial f partial x dx, right, plus partial f partial y dy. What this means, right, among other things, is that m has to be the partial derivative of f with respect to x